for the nice introduction. And even I was very happy that I'm the part of your team as well as here. Actually, this lecture, Dr. Santosh is supposed to take this lecture, but due to some health problem, he could not able to take, and I got this opportunity to take this lecture. So thank you so much, ma'am, for giving this opportunity. And then let me start the lecture. So in today's lecture, I'm going to talk about the deep learning architectures for multi-weather image restoration. So I think audience might have gone through the literature content about the like machine learning followed by deep learning algorithms like architectures, CNN architectures, and in this case, even generative adversarial networks. So different architectures are there. So here I'm especially targeting, or I'm going to talk about the mostly on restoration, which is nothing but regression problem, where image restoration, which is affected by using weather conditions, weather situation, that I'm going to talk here. So in my lecture, I will be covering how we started this research and how we take up to the each stage to the stage by stage, how we improved the performance as well as it's one thing here. Our lab, we are not concentrating not only on the development of deep architectures or maybe for the research point of view. Always we are looking for the, can we deploy this particular architecture, whatever architectures we are developing, can we deploy this for the real world applications with the very less computational complexity, at the same time commercially means it should be commercially viable in terms of accuracy, at the same time in terms of efforts. So here multi-weather image restoration, it is a very much important and pre-processing step for all types of, means any computer vision algorithm. It may be high level computer vision algorithm like object detection or semantic segmentation. So any kind of computer vision algorithm, especially this is a kind of pre-processing step, is essential because we are trying to deploy this content or these models in, especially in the real world applications. It is in outside the environment, which is nothing but it may be affected by haze or maybe by rain or maybe by snow. So is there any occlusion here? I think I will minimize this. Yeah. So here weather generally degrade the images or maybe videos which are collecting from outdoor scenes. So you see here it is affected by haze or fog here. The visibility is slowly as the distance increases from the camera sensor, the visibility is decreasing. So I will be explaining in the next slide how image generally captured or how this image formation is happening, that I will be discussing. But here point is that when distance is increases from the camera sensor, here somewhere we are having camera sensor in this portion, and when we go far distance point of view, so the visibility is decreasing. This is because of content degradation when distance increases. So that is the main problem. And another thing is like rain you see here, this is the rain related, means when you acquire the data or images in rainy situation. So that time also it is getting affected. Here we can see not only rain, you are able to see some veiling effect, which is nothing but rain plus haze together are occurring. So another case like here, you can see here, this is a snowfall. So snowfall also affects the surveillance system. Let's say if I'm deploying any kind of surveillance system, it may be for object detection algorithm or maybe any other kind of moving object segmentation. So there definitely this snow content as these snow particles definitely will affect the accuracy. So which is a major difficulty when we deploy our solutions in the real world or outdoor scenarios. So these are the major problems, and at the same time, if you see here, this not only snow, it can create some kind of haze also within that also. So so it means your outdoor scenes not only affected by individually by haze or not by only rain or by only snow. It can be a combination like rain plus haze or snow plus haze, like the different combinations may also possible. So because of this, it reduces the interpretability about the data, whatever image or video you are acquiring. So if you want to go for a high level computer vision task, the performance definitely will be degrading. That I will be showing in experimental manner only, how this is going to degrade in the experimental analysis point of view. In those slides I will be explaining. And now coming to the how image generally acquired, how we are capturing our image using camera sensor. Let's say I am having a mobile phone. Using this mobile phone, I am capturing the photographs. It may be a photo or maybe a video. So generally what happens, let's say this is an object. So this is an actual object and it is illuminated by the light source. So once it may, here I am assuming it may be a some kind of light source or maybe a sun or anything which whatever it is may be the case. But this is illuminated on this. So once the light fall onto the object, so the amount of light per unit area strikes the or hits the object, that is called illuminance. Illumination is nothing but light fall onto the object, and the area per means the amount of light per unit area is called the illuminance. Once the light is fall onto the object, so this light will be reflecting in all directions. So this light is whatever light is fall onto the object, it will be reflecting. So this reflected light move towards the means move in all 360-degree directions. So once you see here my hand, so you are able to see my palm this side. So you are not able to see other side of my hand. Reason is that whatever light is reflected from this one, it is moving towards the camera sensors of my laptop, so that you are able to see it. And whatever rays are moving towards the other side, so that is not reaching to the camera sensor. That is the reason you are not able to see this portion, back side of my hand, you are not able to see. So this is actually even, it actually reflects in all direction. Whatever light is fall onto that, it is actually reflected. Once, but when you are keeping the camera sensor within the line of sight, so within the line of sight, you are able to capture it and you are able to see that view only. So that way you are capturing the image. So what happens, let's say this is an object, object region, and here some camera we kept here. So this light is started moving towards the camera sensor. So when we start moving towards the camera center, it needs to travel certain distance. So that distance is generally, if you assume this is a capital D distance, it has to travel. So that too here medium is maybe different here, means generally for a outdoor scenes case, it is a haze only, means like air is only the medium. When it is started moving towards the camera sensor, so it travels a distance of T. But you assume there is a air particle here, means there is a dust particle or maybe a kind of water particle due to some moisture. So this is an water particle. So the reflected light when moving towards the camera sensor, moving towards the camera center, it will try to strike the water particle. Then it loses the energy, means whatever light reflected and hits the obstacle or in between the some particle, here I am taking as a water particle. So definitely the energy of this light is absorbed by the water particle. And attenuated light, it means total energy is not with light content, it is absorbed by the water particle. Then it is starting even attenuated light, it is not 100% absorbed by the water particle. Let's say it is absorbed by 20%. Okay, 20%, then 80% of light is again moving towards the camera sensor and it will reach to the camera. So now you understand. So when distance between the object means seen and the camera, if distance increases, so it needs to travel long distance, and in between there are so many particles may present, and because of that more attenuation may happen. Because of that, whatever the light is reflected from the object is not able to reach to the camera sensor 100%. Slowly, even in between some particle is there, again it will be absorbed by that particle, so that it may be 80% becomes 60% only, and so on. When distance is increases, it is not able to reach the good information. It is trying to absorb by the medium particles. In medium, it may be air particle or maybe a dust particle. So then another one is that is moving towards the camera sensor, and it may be a percentage of 60% or maybe 80%. So it depends upon the distance. At the same time, when this particle is water particle absorb the energy from the light source, reflected light, so this particle itself behaves like a another local light source. So this content, this particle will itself is behaves like a local light source and moving towards the camera sensor, that we call it as air light. So because of that, resultant hazy image will be equal to actual clean image into transmission map, which is nothing but inversely proportional to the depth. Okay, when depth increases, percentages decreases. Transmission map is inversely proportional to the depth. When depth is more, transmission content reaching to the camera sensor will be decreasing. So when depth is less, content reaching to the camera sensor is optimized, means it will be as large as possible. So that is this one, first one. And then as I said that each particle behaves like a absorbed particle behaves like a local light source, and that is moving towards the again camera sensor, and because of that this part is coming, and overall we are assuming that the image formation is in terms of two parts. One part is like attenuated light moving towards the camera sensor, and absorbed light, absorbed information or absorbed energy by those medium particles again behaves like a light source and reaching to the camera sensor. Because of that, you are able to get the image with two particles, means two parts. Okay, this is actually the physical model or atmospheric scattering model we call. So even this is happening in all image acquisition models case. It may be in indoor, or it may be outdoor, or it may be underwater. In underwater case, medium is getting changed to water instead of air. And then in rainy time, medium is air, but rain is there in between as a droplets, or maybe it's a line of rain. So these are all the problem. Because of that, what happened? Visibility is decreasing. So see here, this is actual image if I collect without rain, and this is the image if I collect rain plus haze. And then this is the actual image if I collect without any problem. But when I collect it with the rainy image, the rainy content, this is the image. But now coming to the point, like in our research, how we can get, means it is an under constraint problem. This rain removal, haze removal, or snow removal is an under constraint problem, because you cannot collect two images at same time with rain, with degradation and without degradation. It is not possible, because if you collect a photograph with a certain location without rain and then keep aside, and then again we are, let's say if you are applying rain on that, maybe artificial rain you are applying, it's some setup you did and rainfall is coming, again you are collecting. So both images are not at all same. Even if you collect a photograph of say any scene with few microseconds difference, still both scenes are both scenes are having difference. So that is the main problem here. We are not able to acquire the we are not able to acquire the two images with both conditions, without effect or with effect. Means like a clean image and like affected weather degraded image, both cannot be collected. What we are doing, researchers, we have to train our deep learning model. What we are doing, so there are some good depth estimation methods are there. Using this while training of our algorithm, for training data generation purpose, we are taking clean image, and for that clean image, we are calculating the depth. We are estimating the depth, and estimated depth is nothing but it is inversely proportional to the transmission map. With that we are getting the transmission map, and image is there. Using this distance and this and another rainy content, based on that we are adding the rain plus haze also in between, so that we are able to generate the rainy image synthetically. So now you can see here we are adding the rain based on the depth. So if you observe rain case, when distance is increases, so rain content is increasing. At the same time, haze content is also increasing. So because so much content is so many rain lines are coming, rain stacks. Because of that, visibility is decreasing. At the same time, haze content is increasing. So we are generating the data this manner, and we are using this data for the training purpose. So in the same manner, snow addition to the data we have done this way, like this is a image and then we have added snow. Generally snow may not be work out with depth. So it's like you can add directly. There is no need of depth information for snow. Actually hazy conditions you need the depth. Otherwise in the snow condition case we don't require of depth. So based on that, we have generated snow image and without snow both, and this data is used for the training purpose. And haze addition is like this is the image, and then this is the depth, and based on that we are adding the this is the transmission map, and with this you can see here. So we will add more content in the when distance is more, and based on that we are adding the content. This is the resultant training data which is collected or which is generated by ourselves. So even we can take up the questions in between. So ASM is means atmospheric scattering model. So even I have explained how this is acquired these images. Okay. So let me continue. So coming to the applications. So coming to the applications case, you can see automated surveillance system, all weather surveillance systems we can develop, like all outdoor scenes, whatever CCTV footage is installed in outdoor data collection. So that time definitely this kind of haze removal or rain removal problem is an very much essential pre-processing step. And this data may be used for other high-level computer vision tasks. It may be for object detection or maybe number plate detection. So these days now our traffic lights are even in roads. We are deploying, means like our government deployed the many CCTV footages on road, and so that number plates can be detected even weather situations when bad weather conditions are there. That time also, if we are able to collect, or even night vision cameras are also they are deploying, so to work them in the night time. So this is one thing, and other one is like autonomous driving case. Autonomous driving case, you need depth as well as visibility is also very much essential, and at the same time it is working for the object detection. So you need, even sometimes it needs to go for the depth also. How far the object is there in front of the driverless car, so that based on the distance it should apply the brakes and then it should stop, or it should avoid the collision with other vehicles in front of the autonomous vehicle. So like the depth information, like so many algorithms are essential here. Even computer vision is very much important here. So, but for all these computer vision problems, this pre-processing step is very much essential. And now coming to the object detection case, like whenever you are going for the object detection, if you go directly, it may be a problem. But if you go with pre-processed data, definitely the accuracy can be increasing. I mean, accuracy definitely will be increasing. And another one is like automatic means number plate detection. So number plate detection is also affecting because of weather degradations. And another thing is the depth estimation. Autonomous vehicles case depth estimation. It may be based on stereo depth or maybe a single image depth. It depends upon the how many cameras you are using. So, and if it is stereo, still you need to go for this pre-processing algorithm of haze removal or rain removal or snow removal. These are all pre-processing steps. We need to. These are all applications of our work. And then even if you see, let's say this image, and we have gone for the object detection, car detection. Of course, car is detected, but confidence level is 71% only. But if you see here, confidence level is 90% here once we apply the deraining and then give into the computer vision application. So the application of object detection or car detection here. At the same time, if you see here, sign detection and stop sign detection or maybe any nameplate detections is definitely affecting because of that. And another thing is depth estimation. You see here, once we estimate the depth with bad conditions on this image, you will be getting this kind of depth. But once you go with the cleaned image with our pre-processing algorithm, these are the results. So accuracy of these methods can be improved drastically by applying these restoration problems as the pre-processing steps. So this is the main motivation for starting of multi-weather image restoration problem. So with this motivation, actually we have started our work in 2017. Even we have started this work with funny manner because I'm from Ropar, IIT Ropar, India. So here actually in winter season, here visibility is very less. Even you can see this Delhi region and Punjab region, which are affected by stubble burning, and so that in rainy or winter season, the visibility is decreasing, and it sometimes it's a less than 1 meter or even less than 1 or 2 feet also. So very dense haze is present here. So actually I got 2 PhD students in around August 2017. And then we thought of starting some research problem. And then again, I mentioned that we should start a research problem which is able to work out. So the question is that I think the distance between camera and the object. Okay. So I think I will take up all these questions maybe 15 minutes before of my lecture. And if anything, if you feel it is very much essential for the next level, you can ask me immediately. I will definitely take up those questions. So this is the main motivation. Even as I said, that student joined and I said that we need to take up a research problem, which is applicable to immediately to the real world problems. So with this he started, and then as August and by September end we got this means that time winter, and then I mentioned to my student that why don't we start the fog removal. Then he started searching the literature, and by that time itself we are having a few publications. So even top publication in CVPR was also published, that is dark channel Prior. It was very popular, and it was proposed by Kaming. He's a top researcher in the field of computer vision. Even like Resnet proposer or RCNN. So like that, even in this field also he contributed, and he proposed a dark channel prayer. So with that work, we have motivated and we started working on that. And then with this, we could able to publish very good papers in later years after 2017. And then we got a publication in 2000, even other publications in between. And in 2020, we got a paper in CVPR 2020. CVPR 2020. The title of that paper is Very Colored Image Dehazing. So before that also we got some papers in WACV, WSCV, Winter Conference on Computer Vision, Winter Conference on Applications of Computer Vision. So we got a paper in 2018 immediately, like 2018. It means we have submitted a paper in end of November when we started our work in maybe end of means around September starting, and we could able to get paper. And then with that enthusiasm and motivation, we have worked further and we got this. So before 2020, all people are working with a certain colored haze, actually only specific colored haze. It may be a blue colored haze, or it may be like morning time you can see different colored haze generations are there, like when sun is about to come, that time it is a red shade is there, and evening time it's some kind of blue shade will be there, and after some time low light will be there with this. So the different types of hazy conditions, and even when you collect the photographs in the morning and lunchtime, and even dinner time is evening time. So at the water bodies, the colors or shade will be different. These hazy content colors will be different. But no researcher thought in this direction that why don't we handle with a single model to solve all these problems. At this point only we propose a problem like very colored haze removal problem. We have developed a generative adversarial generator architecture using GAN. So in that we are handling with all types of hazes, like all different colored hazes. Like you can see here, it is different color. This is maybe similar color, but this is different. This is white color. This is somewhat pink color. This is yellow shade is there, and here also some yellow shade is there. Some other colors also there. So even miss in this data, this is the input data. So these are all the different types of shades are there, and our target is that we should able to restore this data in pleasant manner. So that is actually the requirement, and even this was the first paper people targeted on a single model with multiple colors. So that's why we have given named it as very colored image dehazing. So and then here very colored case, very thing is that very important thing is that chromatic cast needs to be adjusted with different hazy conditions with different colors, and then at the same time visibility has to be improved. So it should balance the color. It may be a green color or blue color shade is there, but still you should able to get the restored image should generate the appropriate content. If you see here, this is having kind of yellow shade, but if you see here, this content is almost wherever it is essential greenery is there, green. So greenery portion having green and other portion having other content, means appropriate content. We are able to restore it using our algorithm. So, but here we have done this in two stage implementations we have done. So the first stage is that whatever image is there, so there is no removal of haze in the first module. Generator one is not for the haze removal problem. It is a color correction or color balancing. So even whatever the color you give, it should convert that to the white colored haze. So that is the way actually. So what we did here, we have added means a clean image we have collected, and from that clean image we have added colored haze, and then at the same time white colored haze. So different colors haze and white colored haze on the same image. So then we have trained one generator for the color correction. Whatever the color input you are giving colored haze, so that will be corrected to the white color only. And once we did this, then task of restoration is done using another generator network, and we are able to get the accuracy in very appropriate manner, means accuracy wise, but I'm not talking in terms of numbers here. If you need more information, you can go through this paper. But here I'm explaining more intention, means more motivation, how we developed this algorithm, because initially we have tried using single network to address all these problems, like instead of color correction, so directly it should correct the color as well as it should remove the haze. So we have tried using single generator, but it is not working. So for that purpose only we have developed one generator just for color correction, and after that visibility improvement or visibility restoration module. Like the two modules we have considered, these two modules are trained differently in disjoint manner, because that time training of two models, because this research of deep learning has evolved very drastically, means very faster manner. So when we use 2018, that time we don't have much computing resources, and now we are able to get GPU of even 48 and even more 80 GB GPUs. NVIDIA is able to launch. So that time highest was means it is available to everyone is 8 GB GPU, and then DGX station is having 16 GB GPU only. Each GPU memory is 16 GB. So that is the reason we have trained it separately, but with current technology we can do in end-to-end fashion also. We can train using regularization here, one regularization for color correction, another regularization for the restoration problem. So like that we can work out here. So with this one, implementation, this is an architecture. So in this architecture also, I will be explaining how this is different and how it is good or important for the restoration. So actually, people think that this deep learning is a black box, and directly you are handovering the task to the system and automatically it will work out. If you want to get the result around 70-75%, yes, you can go as a black box. So up to 75% you can able to get it. But if you want to improve the accuracy beyond 90, so you need domain expertise. So you need to know the computer vision concepts, actual computer vision concept, image processing concept, then only you can able to improve the result. So one example I am giving, let's say this is an image, and on this image, this color correction part, pseudo color generation case. So what we did here, we have taken R, G, and B components. So as this is a color image, we have collected R, G, and B. And on this, we have collected 16 frames, means the 16 channeled output. 16 means using 16 filters, we got this. And similarly, red, green, and blue, all three channels we have acquired. So here there is a motivation, like dark channel prayer is not a deep learning based algorithm. It is a very fundamental and very basic concept. It was utilized and it could able to get very good results. So how to get the depth of the image? So it's a very simple manner it is implemented. So let's say R, similarly G and B. So we are having three images. So means one image only, three channels. So let's say if I assume if any pixel, means no pixel is affected by haze, it means these are all synthetic colors. Assume that synthetic colors means no loss of information at all. So that time it's very clean, means you can say it is a clean image. Clean image means all colors are appropriate in the image. So that time if you take any color except black and white, if you see any color, so these colors having means out of these three except black and white, one value will be closer to 0. If you see any red color, red equal to 255 and green and blue are 0. If it is yellow color, red green will be 255 and blue equal to 0. If it is a blue color, R and G will be 0 and blue color will be 255. So like that it is getting, even if you take any color, which is a synthetic color, and other than red, other than black and white, if you see, definitely one channel will be having closer to means value close to the zero. So with this assumption only, so we are saying that whether it is whether this pixel is affected by haze or not, we can able to say. Because let's say when it is affected by haze, what happens? So even red green, like a red color is there, red color is affected by haze only, but it is already 200 or 255 because it is red color. So that value may be improved by somewhat higher value, because it is a white shade or white colored haze only happening. So when you talk about the green and blue, because it is a red color image is there, object is there in that image, but green and blue components are zero. So that time what happens? This haze definitely affects that region also, and that is not a zero value, it is a higher value. As haze is having white color, it is not a white, it is not close to zero, G and B. It is also close to more than 150 or 100, it will be like that. So if I get the minimum across the channels, so from this I can tell whether this pixel is affected by haze or not. Like if I take one pixel here, another pixel here, another pixel here. So if I take the minimum of these three values, so if this minimum, it get fails, just understand, it get fails at brighter objects. At the same time, it fails at the white objects as well as black objects, because black means all are zeros only. All are zeros only. So all are zeros means if you take the difference of that, means minimum of zero, it will be zero only. So that time we cannot say that pixel is a clean one, or even if it is affected by haze, that value will be greater than zero only. So that time also you can see. And when it is white particle, all are 255, and even if you affect it by haze, so it won't be affected by the haze because it is white, it means all are 255. You know, whatever the content you are adding on top of that, it will be 255 only. Okay, so with this assumption, dark channel prior was proposed. So we have taken that dark channel prior concept. So as we applied this dark channel prior is converted to deep learning model. So what we did, R channel, G channel, and B channel we have collected, and with that 16 channel responses we collected. After this, R channel content first channel, and in this also first channel, in this also first channel. So I have collected these three, which is looks like a pseudo color image, you can say pseudo image. And similarly we are getting other also, like 16 channels are on this, and I will be getting 16 pseudo color images I am able to generate in this. Okay, in this, and then even that time only attention mechanism was just started. The attention mechanism was just started. And even there is a gray old assumption is option. One gray old assumption is there. It is like maximum. There is a formula for that gray old assumption. If you want to that, you go through that formula. Formula is that max of average values of red channel, green channel, blue channel divided by average value of that channel. Means it may be a red channel if you are collecting this value for the red. So based on that, all color corrections are happening. So we are assuming like this is trying to correct the color. So once the color corrections are done, all are concatenated and again applied some convolution layers. And here we applied a regularization for the colored haze becomes white colored haze. So single colored haze, which is a white colored haze. And then after that, we have given this to the encoder architecture, like 32 channels and 64 channels and 128 channel with downsampling by 2. And after that, this content is used, and again here we added the attention, like channel attention mechanism and spatial attention mechanism. So it was like, you can say, around that time only the attention mechanisms were proposed, and then we adopted this attention mechanism immediately for this our model. And then after that, we are going for the decoder module upsampling model. And here we are calculating the loss, that is haze-free image generation. So this is the network architecture for very colored haze haze removal problem, varicolored image dehazing problem. So now coming to the experimental results, when you see this is an input image and these are the results by other existing methods like CBPR 18, CCC 18 and CBPR workshop 19. And then this is our work, that is nothing but CBPR 2020. So this is of CBPR 20. So similarly, we have verified, we did not train anything on the low light data. So just we have gone for the testing, which is we want to take it as a cross data set evaluation purpose. And we have taken this and we are able to restore the haze as well as night vision can also be appeared here. It is getting improved visibility in the night vision content also. So this is a kind of advantage, I would say. It works. And if you see here, we have applied this algorithm on the very dense haze content. Here you see very dense haze is there in this image, and once we apply this is the output. Of course, there is a small kind of distortions are there in this, but see here visibility how good it got improved. And if you see with other existing method, it is having so much color distortions and it is not able to work out well for this. See here in this pink color haze is there, and this when we apply with our algorithm, see it is able to correct it, but other existing methods, as they did not consider the color correction before processing the removal of haze, so they are not able to work out better, but ours is able to generate very pleasant image, pleasant results. Even for the tree case, it is greenery, and objects case, it is having appropriate texture content. So these are all the results with varicolored image restoration, haze removal problem actually. Then we have extended this work for the means a similar kind of work we have extended for the rain removal problem. So it's actually for deraining in videos. So people are in deraining also, people always working like they are developing like different types of architecture they have developed. What they did, they have used different stages like stage 1, stage 2 and so on stage n. It may be using the combination of convolution layers followed by activation functions or maybe pooling layers and so on. So it is happened, means people are doing, and at last it is actually this portion is like rain estimation. Rain stacks or rain sticks estimation is done in literature, and then it will be subtracted from the either maybe input image or maybe some stage result in between, and then so that you are able to get the haze-free image in that too in progressive manner. But see here they are subtracting this at the end only. But we assume that we felt that if we apply this algorithm in between also, this separation like this, see here, this is the case, and we have subtracted here, and then output is there, and again further process like that here, n number of times we are applying, it is progressively, it is improving the restore, means improving the visibility. So that this way we have motivated, and with this we have started and we have developed this algorithm of encoder decoder architecture for rain removal problem, that too video rain removal problem. And this paper got published, this particular our work got published in IEEE SPL, signal processing letters. And then as it is a video processing problem, in first frame case, we don't miss, we are having first frame only, that time it will be processed as a single image. And whenever we are processing from the second image onwards, second frame, so that second frame having this some kind of feedback from the first frame also we can use. Like first frame content is with us, so that content is feeding into the second frame in between also, so that we are able to get the output data, which is restored data. So because of this, it is a recurrent content concept we are developing here, and because of the temporal consistency, it can be maintained in the video processing. So because of this, now we are able to maintain the consistency in the videos which are restored. So here we have considered different types of architectures with multi-scale, multi-kernel, strategies and different type of strategies. And another thing is that we have experienced and we have experimented different ways, like if I apply downsampler and upsampler, so directly, so the performance actually it can able to remove the rain or haze or fog, sorry, snow, but other objects also getting affected, even object clarity is missing. So because of that, what we did here, we have applied downsampling operations and we got the results, but at the same time, at the same scale, we are processing. So whatever the loss of information happened at the downsampling operations, so this loss of information again will be compensated using single stream there without any downsampling, that is this stream. And then this is the downsampling stream we are performing. Together, all are concatenated and given for the final results calculation. Because of this stream, we are able to get the good texture content, and because of this content, it is able to work out or remove the large amount of haze or rain which present, means density wise, more when more dense data is there, we are able to restore it properly. So this way we have motivated and we have started working on this, means working on this particular problem, and then we have compared in terms of runtime. You see here, it is NC is not means it is not compatible actually, and NE is not executable due to out of memory error. Out of memory error means these networks are very bulky, and then these networks are very bulky, and then accuracy wise these are also not appropriate. So here you can see here our algorithm having runtime is 38.38 seconds per frame. So which means I'm able to process around 2.5 frames per second. Around 2.5 times per second I am able to process, and here parameters ours is 0.24 million parameters, which is nothing but just 2,40,000 parameters only we have developed here, which is deployable in the commercial applications point of view. That's what we are saying. Our algorithm, whatever we are developing, this algorithm can be deployed in the models, and even we are trying to work out for the Android app developments also. So we did one project on haze removal sponsored by Indian government DST, and there actually we are making the Android apps, and with these apps also with the Android apps we want to deploy, means like we want to develop a add-on for the cars industry. Like as they are already keeping rear camera, we will keep front camera, and with front camera it will be connected to the dashboard, means that screen, and within this screen we will display the restored data, so that in extremely dense conditions, so driver can utilize the screen data, which means screen content which is restored, where visibility improved as compared to the existing, so that we are able to utilize it. We already developed this model, and this is ready to deploy actually, and it is now the add-on cost is between 15 to 20,000 rupees only. So because if add-on cost is 1 lakh rupee, who will take this add-on to the people, those who are taking new car? So that is the reason we are making this algorithm for 15 to 20,000 at this moment for development of single model. But if we go for bulk production, so even it can come down to even 7,000-8,000 rupees, or even less sometime when we go for bulk production. So this is the main advantage means we have developed here. And if you see here rain removal, I'm showing here results with so here you can see here, this is input content, and this is a ground truth, and this is our algorithm. It can able to restore it properly. See here, you can see this is rain content, it is added, and as rainfall is there, and it is able to restore using our algorithm. Ours is still sort of inconsistency is there, but So some inconsistency it may be there, but results are relatively far better as compared to existing algorithms. See here. Here some small disturbance is there, but however it is performing good. So here also still some rain is there, but it is able to work out better as compared to other existing methods. So these are all some of the results we got on that video deraining algorithm. So as I mentioned, our main target is that it should be deployable. So we have deployed this algorithm in Jetson Nano, NVIDIA Jetson Nano. It is having 4 GB GPU COM GPU, or it may be a CPU. We can use it as a GPU or CPU together. It is depends upon our requirement. If we are passing any graphic content, it can be considered as a GPU. Otherwise, it will be a CPU. It is very simple, means very small computer. It's very small one. It is size is even half of the mobile phone. Jetson Nano. If you guys already have seen this, already if you have seen, I think that is fine. Otherwise, the size is half of the mobile phone only. Okay, and we are able to deploy this and see here real world results. We are able to work out, like display this left image with rain, and this is the image with rain removed image, which is processed using this NVIDIA Jetson Nano. So the specifications about Jetson Nano is a small and portable processing unit, and can be powered even with a power bank also. So you can keep this on drones also if you want to process content on drones. Like if you can keep the weight also, it is very less, and you can directly using power bank. You can deploy this model even in unmanned aerial vehicles, UAVs, or maybe drones. So can be powered even with a power bank, and can be used as a computer with a giant Linux OS. It can be it is I can say the size is very small, but the performance is somewhat closer to the Core 2 Duo computer. Core 2 Duo computer means it was there around 2008 or 2009. Means between that means between 2009 and 2010, Core 2 Duo computers were there, and it's like even at the time of my PhD it was there, and I did my PhD with a Core 2 Duo computer only. It means the similar size. Day by day, this size is decreasing and capacity is increasing. NVIDIA Maxwell 128 core GPU is there and can be connected with internet and also support memory card storage. You are able to use 32 GB memory card we have used here, and it is having USB ports, power supply, and so many things are here. So this is really good Jetson Nano, and this we are able to deploy our model in this. And the challenges with existing approaches like weather specific applications. So people are targeting here in this up to this point. We have targeted for haze separately, rain separately, and separate feature processing has done, and higher computational complexity is also bit higher, because if there is an image with rain and plus haze, so researchers up to that point, researchers were using first they have processed the rain removal followed by haze removal. So two algorithms are cascaded in that fashion, like it is a rain removal followed by haze removal, or maybe vice means other side, haze removal followed by rain removal. Okay, so now this way they are working in the cascaded manner, but cascaded manner working is always problematic. Accuracy, overall accuracy, definitely it will decrease. Let's say if I'm assuming this is 90% accurate and this is also 90% accurate, overall architecture is 81% only, because both are cascaded. So this is a big problem when we go for architectures in cascaded manner. So that's the point we motivated and to avoid usage of separate architectures for various weather degradation. So we have proposed a network like ViperNet aims to restoring this degradation image using a multi-purpose network architecture. And it is even single different architectures. It was proposed for different application. But here we thought, why don't we use this for application means like our application. So this paper like ViperNet, a lightweight restoration network for enhanced surveillance applications. So this paper got published in IEEE transactions on industrial IEEE transactions on ITS intelligent transportation systems. Sorry, IEEE transaction intelligent transportation systems. So impact factor is now, I think it's around 10 point something. So it is having very good impact factor now. So around 9 or 10 it is there now. Okay. So and then here coming to our methodology. So we have developed different types of multi-scale kernel or multi-kernel based algorithm. And here input image is there with rain, and it is a rain restored image. And then what is MCARB? That is a multi-scale context aware residual block, multi-kernel fusion aware residual block, adaptive varying receptive fusion block, like different types of blocks are there. I will be explaining what are these blocks in the later slide, and at the same time one stream is going as it is and other stream is working for the high frequency information, like whatever content is there, it is subtracted here, and again here it is subtracted, and again here it is subtracted. Like these are all the subtraction operations is performing so that it can able to refine the high frequency components, which are nothing but edge components for the restoration point of view. So this way we are able to implement. This is a kind of generator model. And if I explain what are the importance of individual modules, first one is context aware residual block. So the aim of this context aware means like it's not only like I'm taking the convolution layer and depth wise convolution, and then in these two responses I'm taking the max condition, so that it is useful context or useful texture content only will be highlighted. Aims at extracting the detail rich contextual information, and then we have utilized to decrease the computational complexity for the training or testing time. We have used depth-wise convolutions. And it is channel content means it is a dimension reduction, and sometimes it is also performing better. And then strided context aware residual block means here as the degradations have different dimensions. So we need to process with multi-resolution analysis or multiple scales, which are nothing but different sizes of images if we process, so that we are able to we are able to restore the all types of degradations. So these degradations may be with different sizes or different scales can be addressed here. So that is the reason we have developed multi-scale. Even again here also progressive concept we have introduced. Strided base and strided context aware residual block is got proposed here, and another one is like one more point here. Let's say you are having two convolution layers, and a convolution layer with kernel size of 3 and convolution with kernel size equal to 5 by 5. So then we got the result here x and y. So some people what they did here in literature, what they generally do, x plus y, sorry, x plus y, it may be possible, or maybe x concatenated with y and then processed using convolution layer. So are here x plus y and processed using convolution, like various combinations are possible. But here what we did here, we have developed some kind of learnable parameter, because x plus y means 1 into x plus 1 into y. So it is giving equal importance to the both weights and giving the summation. That is one way. And another way is like concatenation. Concatenation case, it is working with different importances will be given overall in the image format. But here, if we go with trainable tensor, we are taking a tensor, and in this tensor, we are applying like a sigmoid function so that this value is coming between 0 to 1. In this 0 to 1, actually, so this is a learnable parameter, and using this parameter lambda and 1 minus lambda. Lambda is multiplied with d1 and 1 minus lambda is multiplied with d2, and then both are added here. So because of that, you can see here the how much addition is performing, contribution between d1 and d2 is identified in terms of in dynamic manner. So this is really performing good, and we have considered this problem. So means we have added this new contribution in this, and with this we are able to show the better accuracy. Even ablations were conducted on this basis also. These are all the feature refinement stream, where we are going for the refinement of further level. Even multi-scale and all these things are utilized here. And at the same time, channel attention and spatial attention, two types of attentions we are using here. And using these two attentions, as I have explained in very colored image dehazing, there also we could means we propose channel attention and spatial attention there. But this data, even these results we got, I think this paper got published in 2021, I guess. So even it is around 1.5 year old. That time the attention is very much matured, and people are everyone started using attention mechanism. When we did our 2020, that time very few, means even less than 10 papers were published using attention mechanism. But here by this time, even attention mechanism has matured, and it's got evolved with the good outcome in terms of accuracy. So that's why we also adopted here attention mechanism with us. And so if I apply this for real world analysis, like a results point of view, if I take this is rainy image, these two, and then corresponding, these are our results. The visual comparison of results on rain 100 data set for rain stack removal. And similarly, this is for visual comparison of the results on raindrop data set for raindrop removal. So raindrop is different and rain is different. Rain is like lines, it will be falling. But raindrop means like your car is there and rain has come. So you are sitting inside the car and driving. So, but whatever the particles fall onto the mirror, means like glass. So front glass or maybe side glasses. So those some kind of water particles will be there. This we call them as the raindrops. So these raindrops again degrade the scene. So that also we have addressed, and we have implemented our algorithm to train on that particular problem also. And even visual comparison of the results on RS data set for rain stack removal. Rain stack means these are in terms of lines, and it is able to improve. Ours is better than ours is the better than the even other existing methods. So this way I can say our method is outperforms other existing method in terms of even visual analysis here, and at the same time we have given quantitative analysis in the paper. So you please go through that. It is in IEEE transactions and intelligent transportation systems. And then these are all the case like visual comparison of results on RDS dataset for rain stack and raindrop removal. Okay, rain stack and raindrop removal. And then these are all the results further. And then again, we have tested our algorithm on like very densely, like this. You can see here, it is having rain is more, and we are able to restore using our algorithm. You can see here, maybe small lines are, but it is far better than the existing content. And these are all number of parameters. As I said, whatever we are developing, always we are thinking to deploy it for real world. And here we have developed an algorithm with number of parameters of 0.31, which is 3,10,000 parameters only. Even there is a prenet that runtime, but here's a 0.16 parameter means 1,60,000 only, but runtime is 0.18 because number of flops. These means that time people are not showing the performance or computational complexity in terms of gigaflops, gflops. That time they were not showing, but now people are started showing the performance means versus complexity. So gflops, even if you see here, runtime is more as compared to here, but the number of parameters are less here as compared to 0.31 million. So from this only I can tell that number of parameters only not the matter, and it requires to work out with the processing speed and as well as gflops for running of this model. And then coming to the applications part, what we did here, we have taken one image and we have got the semantic segmentation. So if you see semantic segmentation, this content is segmented, but confidence level is 91%, and here 79%. But when you see here, this one 99, and even in this some kind of occlusion content is there, that may be the reason. But if you see here, this one, even this is 99%, where here 79% only. So which is actually far improved, means results wise it is improved significantly. And here is nothing kind of thing is detected, but here you can see here it is detected because of visibility restoration. And similarly text recognition. So text recognition case, whatever the signboards are there, and those signboards can be processed and we are able to perform. So see here, we are able to read this even after pre-processing of our algorithm. And then depth estimation is again a very much essential thing. It may be a stereo depth or it may be a single image depth. So see here, you can see if I process using this image and it will be the output, but when I go for restored data for the depth estimation, this is the results. These are having far good results as compared to other existing methods. And coming to the summary of work up to this, like we have tried for multi-weather, means single architecture for various problems we want to use. It may be for rain or it may be a raindrop removal. So different combinations, but trained separately. So this is idea started moving towards the direction like, why don't we use a single parameters for all problems? Like what we did here, we have trained on differently, architecture is same, but trained differently on each architecture, each data set. But again, we started thinking in other direction. Why can't we develop an algorithm which can solve all three problems together? Like it may be a rain, or it may be a snow, or it may be a haze, or it may be a combined versions. So we developed a unified multi-weather visibility restoration algorithm. We have developed here. This paper got published in IEEE Transactions and Multimedia. IEEE TMM, Transactions and Multimedia. Okay, and here main motivation point, I said that as I mentioned, rain removal separately, haze removal separately, and snow removal separately. And if I cascade one after the other, the overall performance will be degrading. So instead of that, if I go with instead of processing separately, and so with the processing, performance is degrading, at the same time complexity is increasing, because one model, let's say this is having 2 million, and this is also another 2, and this is also another 2. It is overall will be 6 million, which is nothing but computationally very expensive for the real world applications and for deployment of these solutions. So these are all the problems associated with this processing of individual. But here we developed an algorithm with single model of 1.1 million parameter, which is 1/40th size of existing methods. So we are able to develop that algorithm, and then we are able to propose a unified model, it works for the all combination. Here also multi-scale components are there and downsampling operations are there. So this is motivation is very clear, very much clear, that even previous cases also why we are processing one stream is going just to maintain the texture content appropriately, and another parts they like the downsamplers are operated just to restore the content inappropriately. So at the same time, we are also process another stream is also there, and overall this content is restored, output is coming here. And then here this is like a snow image, and the snow will be removed like that. It may be a rain image, a rain, even combined means single trainable parameters of size is 1.1 million only got proposed here, and we are able to deploy it, and we are able to show the results in efficient manner. We are able to produce the results in very efficient manner. I will be showing the results, and even why we have developed these individual models and whatever the importance of these models, all these things you can get information. If you need more details, you go through the paper. Even I can explain, but because of time constraint, and try to cover more content, like where we started from very basic zero module, zero component, and now we are able to reach at to the certain level, like single model should work for all three types of problems. So that is the point here. And again, here also we have used learnable tensor for the fusing of the data. So that's so we have set that adaptive varying receptive fusion block. And then coming to results point of view, you can see here this portion here with hazy conditions, and these are all the results using our unified model. So unified model case we are getting even with existing methods, and we have compared results with unified methods. At the same time, methods which were proposed for individual purpose, task specific. You see here ours is, if I go with task specific only, means separate training if I perform, really coming good. At the same time, even single model is also able to work out. And then here night vision content, like nighttime low light data are trained here. It is just qualitative results on real world hazy degraded data directly. We have not even trained on this kind of content for a single like even like actually haze, rain and snow. This data is there in the training, but this low light content, we don't have data even in the training, but still we are able to perform better as compared to other existing methods. This is for the snow removal and ablation study case with different blocks, with various blocks, how the performance, and those are all visually we have given here, and at the same time quantitatively also we have provided in the paper. So please go through the paper for more details, and if you are having any queries, you can contact us. So this is for high level computer vision tasks like object detection before and after. You see here confidence level. So here this content is improving, like you can see here far better. Only one object is detected here, but you can see here even other object, this is also detected in this side. So that is the power, or that is the importance of our pre-processing step. See here only this portion is detected cause, but a restored content, it is able to improve. So this is actually the important task, and even this portion is not detected, but this is detected. So these are all the kind of advantages on our algorithm, and that too it is a very low light content. Means lightweight model is developed here. See here depth estimation in this particular image, this car. This vehicle is detected, but very shadow kind of thing is there. But here you can see it's very fine level depth estimation happened here. So now coming to the overall conclusion, we have started our work. Even we have developed these algorithms like domain translation algorithms and diffusion models also we have worked, and this content is in under processing for the publication. That's why I did not discuss here, but we have started our journey with a simple optical model, which is nothing but atmospheric scattering model, and now we are able to work out up to a single trainable parameters are able to work out for all problems. So all problems, this is the main contribution up to this point we are doing. and now coming to the point like question case. So I will share this PPT definitely. And then how to predict the performance accuracy in video restoration. Yeah, these are all SSIM values or PSNR values, because whenever you are going for the quantitative analysis purpose, you are adding haze or rain or snow or combined content is in terms of synthetic manner we are adding, so that clean image is with us. So once we restore it, we will go for the PSNR calculation, or maybe SSIM average values of PSNR and SSIM, or we considered as a evaluation measures. Even some other evaluation methods are also there. Those evaluation methods also we have considered here. Okay. So with this, these are all the results you can see here. This is one video collected in Chandigarh Sokna Lake. So we are able to process it very means with very light network, and we are able to give the very good results. See here. See here, very pleasant results it can able to generate. Okay, thank you so much. And if you are having any questions, I can take up the questions. Guys, any questions?
So, I mean, excellent talk, Murala. I can understand the participants may be having some doubts. So first of all, you may ask your doubts, because these things, these networks, like in the first go, maybe a couple of points are not clear to you. So first, you can ask your questions, participants. There is a question here.
Yes, ma'am. I have a doubt not related to today's topic, but is it possible to use SVM for classifying images instead of activation function in CNN? Yeah, miss, before CNN, people used SVM for the classification problem, but SVM is a linear classifier. So linear classifier means it can able to solve for only linear issues or linear problems. But that time SVM was really performing excellent manner. But once you got the miss, always we are getting the upgrades. So CNN deep learning can able to handle even complex problems also, like even your data is not only linear content, it even linearly separable. But if it is having non-linear and complex data also, we can able to handle using CNN. Even we are adding complexity by keeping activation functions. So activation function like sigmoid activation, in deep learning generally we use sigmoid at last only, but in neural network we use sigmoid in between. But here rectified linear unit, ReLU, after that TAN-H activations, people are using in between only. And even we are using batch norm. This is also a non-linear process, so that we can able to make your algorithm is more non-linear manner, so that it can handle the complex problems.
So there is another question. What is motion handling in video restoration?
Yeah, it's a temporal consistency. Once you understand, let's say there is a video. In this video, you are having a haze, let's say. So what happens, I'm taking, let's say video is loaded as a multiple frames, sequence of frames only. I will take first frame and I will process using our deep learning algorithm. Haze removal will be done on that. And then second image will be there. And the second frame, again processed using this. But there is no correlation between two consecutive frames. That time what happens, using your automatic algorithm, first frame may remove certain, let's say 2 frames are there. So 2 frames are there, and then in this frame maybe this portion is removed more and this portion is removed less in this frame. And due to some reason, let's say there is a small illumination variation in the content, so in the next frame, so instead of this, and it will be removing this. So this portion is as it is. So that time what happens, if you play that video, you will see some kind of flickering, like in between there is a light is on and off, on and off. That kind of flickering feel you will get, because my algorithm is not restoring or not removing the haze in consistent manner. Previous frame removed at certain place and current frame is removed at other place. So that instead of apart from the removing, what happening, flickering is coming, and which is actually removing the, or it is not creating pleasantness or possible solution. So that is the reason we can say that consistency. So that motion handling, this even when our objects are moving, so those needs to be handled in appropriately. Otherwise, just boundaries of objects, you will be getting some kind of shades. So even I can means we have experienced this kind of problem. So we have addressed all these things by using temporal consistency, like previous frame output has given as concatenated with the current input, and both are processed, so that previous output is always is trying to drive the current input also, so that it is able to work out in systematic manner, so that inconsistency will be ignored. I hope I have answered your question.
Yeah. So Suchitra Patil is asking, is there any way to assess effect of soil moisture in RGB images?
Soil moisture, ma'am, I think this one is more towards the calibration base, because soil moisture and all these things you can do definitely. So you can take one image and process it, but you have to calibrate. Even we are also working on one problem in our laboratory. That problem is like this motion magnification, like by looking at the face, we should measure the BP. Not only using thermal sensor, temperature we can measure, but we are without any touching sensors. Even we want to measure the BP from the face itself. When person is in tension, so there are minute level vibrations on his face, or even color changes are there. So we are trying to detect them, and based on them, we are able to get. Means in the same manner we are working.
So thank you so much. And Manu Ranjan has written very appropriately that you have actually set the stage, because they have learned the basics till now, and now you have introduced them this, I mean, very impressive work. So I hope those who are new here in the field, they must be knowing that CVPR, right? That is a dream. I mean, publishing paper in that conference, and so and Dr. Murala has just shown you many papers where he could publish and could beat the results of the previous papers published previously in those conferences. So definitely, it is a motivation for all young minds here. And so, I mean, thank you so much for this wonderful lecture. And we are so, I mean, happy, so great. It is so great to have you with us. Thank you.
Thank you so much, ma'am. Actually, this year also we got 2 papers in CVPR, 2023.
Oh, great. Congratulations.